In the last video, I showed, introduced, hybridization and went through 3 examples. Today, I'm going to go through 3 more. One will be an incomplete octet, and 2 will be expanded octets. So hopefully, you'll understand why, something like the SF6 has an expanded octet, or why certain things have an incomplete octet. So we're going to start off with the incomplete octet. So let's say we had beryllium dihydride. Now, this is an alkaline metal, but this one is one of the weird ones. So it can form stuff like this. And basically, if we draw the Lewis diagram here, it just looks like that, right? It's only got 2 valence electrons, and its electron configuration for beryllium is 1s2, 2s2. So if we draw the energy level diagram, actually I need to give myself a little bit more space. 1s, 2s, right? But we're also going to draw 2p because we're going to be moving some things around. So 1s2, 2s2. Now, there are no bonds that can be formed, right? Because these are all completely empty. So, keep forgetting to draw my hydrogens in pink. There we go, to make it look different. There's no place for hydrogen to, put its electrons in because there's no existing electrons for beryllium, right? The hydrogen electrons need a partner from the other element. So there's nowhere to put it. So we're going to do some hybridization here. What we're going to do is we're going to write it like this. We have our 1s here, 1s, and 1s. We put this guy, put it up here. So actually, this would be like that blue color. Now, hydrogen can come and put its bonds here, right? So we would just call this sp hybridized because we have one s orbital mixing with another p orbital to make these sigma bonds. And so you'll notice, there's no full octet here. Beryllium is not making 8 electrons, and that's totally okay because we can justify this through hybridization. Hybridization allows us to justify why certain compounds and molecules will not follow the octet rule. So this is one of them. This is an incomplete octet. So hopefully that made sense. All I did was I used this electron here, stuck it up here, and then hydrogen can come place its 2, and now beryllium can make those 2 bonds like it does in the Lewis diagram. Let's look at a more fun one. Expanded octet. Let's look at wrong color, pH5. So the Lewis diagram for this would look like this. You have our hydrogens here, and I forgot to do it in pink again. I do it in a different color to help illustrate the point a little better. All right. So let's do the electron configuration of phosphorus. So it's a long one. 1s2, 2s2, 2p6, 3s2, 3p3, right? Let's draw it now. The energy level diagram. 1s, 2s, 2p, 3s, 3p, but we're not done. I'm going to draw 4s and 3d because we're going to be doing some promotion here. So like that. So we have another situation where phosphorus in this diagram, in this compound, is making 5 bonds. It's making 5 sigma bonds. Sigma, 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 sigma. But it only has 3 vacancies, only 3 spots to fill. So the hybridization that we're going to do is going to look like this. 3D, 4S, 3P, 3S, 2P, 2S, 1S. Isn't it so much fun to just draw this over and over again? All right. Here's what we're going to do. We see this, in terms of promoting an electron, we can promote this 3s1 here. Nope, did not mean to draw the calculator. This 3s here, we can take one of these electrons and stick it where? Do we stick it in 4s, in here, or do we stick it in 3D? Pause the video and think about it. So, we're actually going to stick this electron in the 3D orbital. And the reason is, well, elements in the third period have an expanded octet, and they have an expanded octet because there is a 3D orbital that they can shift their electrons in. So even though you may think, let's put it in the 4s, not so much. We have to complete, as many of the orbitals we can before moving on. So you know from the previous videos that 3D orbital has slightly more energy than the 4s orbital, but that does not mean we fill up the 4s one first. We have to go in terms of S, P, D, E, F, right? So the next guy that's up is D. So we would take that electron. So if I just write it up all here, 3s, we would stick that 3D up here. And we do this again because just because 4s, is a lower energy level doesn't mean we put it there. We're still in the third row, right? In the periodic table, if you look at your periodic table, we're still in the third row. So we're not going to randomly just put it in the 4s orbital when we haven't, filled up that 3D orbital. So this is what it looks like now. Now, how many vacancies do we have? We have, I'll just circle. What color do I circle with? We have 1, 2, 3, 4, 5. How many bonds is phosphorus filling? 1, 2, 3, 4, 5. Beautiful. So all these hydrogens are going to come in, dump off their electrons, and that's it. So what would be the classification we give this? Well, let's count how many of each orbital we're dealing with. We're dealing with one s orbital, right? Just one singular s orbital. We write 1. We have 3 p orbitals here. And we have 1 d orbital here. So that's the hybridization. sp3d. Our classification is according to the sigma bonds, right? How many sigma/single bonds are we making? So phosphorus is sp3 dehybridized. And this is an example of an expanded octet. So that's really it. So we have this expanded octet, and we have that because of elements in the third period and so on have these other orbitals that we may not necessarily think about, but they still exist. They're there, and so we can move those electrons to those orbitals to achieve the bonds we need to make. Let's look at SF6, very famous example. Fluorines, got our here. So the electron configuration of sulfur is 1s2, 2s2, right? Okay, 1s, 2s, 2p, 3s, 3p, 4s, 3d. Right? 2, 3, 4, 5. So 1s2, 2s2, 2p6, 3s2, 3p4. Three S2, 3p4. So pause the video and see if you can figure out the hybridization for sulfur. All right. So we see that these fluorines here, they're making about, and I'll just circle them in pink, forgot to draw it again in pink again. There's about 6 bonds going on here, 6 sigma bonds. And how many vacancies for fluorine to occupy? Only 2. So what's going to happen here is we're basically going to do a lot of promotion. So the way this promotion is going to look like is this. Three S, 2P, 2S, 1S. One, two, three, 4, 5. All right, 1S like that. All right, so let me draw the 3P like this, like this, like this, like this. So we're gonna take this electron, promote it to, actually let's start off with this one. We're gonna take this 3P1, put it into 3D, right? And then we're gonna take this 3S and well, put it where? Pause the video and think about it. Well, we talked about in just the previous example, we're gonna just put it in 3D, right? Because we are in the 3rd period, right? Sulfur belongs in the 3rd period. So we're gonna stick it up here. So what you end up getting is like this. And now how many vacancies do we have? Let's count. 1, 2, 3, 4, 5, 6. All the fluorines can come and occupy this. And the hybridization we end up with is, well, we see that there's 1 of these, there's 3 of these, and there's 2 of these. So this would be sp3d2 hybridized. That is the hybridization for sulfur. And that's pretty much it. Just went through 1 incomplete octet example and 2 expanded octets. So yep, we are done.